Hey guys, welcome back to Eureka, and in this video I'll be teaching you about derivatives chapter. What does it mean to take derivative of a function and the generalized formula of the derivative. Let's start this video off by drawing a straight line, and I'm just gonna simply ask you to find the slope of this line, right? How do you find the slope of a line? Well, you simply take 2 points on this line, you draw the perpendiculars here, delta x, delta y, and the slope is this hypotenuse, right? And it's equal to delta y over delta x. That is the slope. And this is also equal to y2 minus y1 over x2 minus x1, right? That is what we know about the slope of a function. Now, this can be defined as the rate of change at this function. What does the rate of change mean? That means this line, the slope of this line, the line keeps on increasing by a certain amount every time, right? And that's why it's sloped upwards and it looks like a straight line like this. Now, what if we have a different function? Let's say we have a parabola. Let me just erase these and let me show you. And give me a second here. Okay. Let's say you have a parabola, right? And you want to find the slope of this parabola at a point, right? Let's say you have a point G and you have a point F, right? Let's do what we did with the straight line, and let's just draw a straight line through these 2 points. Now, what can you guys notice? This cannot be the derivative. This cannot be the slope of this function, of the parabola. You guys can see that it doesn't make sense to define this as a slope, because this is a curve and the straight line is a straight line. So how do we find the slope of a parabola, the slope of any function? Well, we define that as the derivative. How do we define the derivative? The derivative is basically the slope of the tangent to the curve at a single point. So the derivative of the parabola at point G will be the slope of this tangent. Let's call it L. Or at point F. Let's draw the tangent at point F, right? Let's call it M. The derivative of the parabola at point F is the slope of the tangent M, right? Now, how do we find the equation of a derivative? How do we find the derivative of a function, right? So let me just redraw this parabola and let me label some points with different colors. Let's say you have a point here and a different point here, right? And let's just put the x value of this point, call it xg, and the x value of this point, call it xr, right? And now let's just draw the line between them. It goes like this, right? Like this, right? Now we want to get to the tangent at point xr. We want to get to this line here, this small tangent here. I'm just gonna draw it like this, a very, very small line. Let's I have an idea. Let's get point xg closer to the red point. Let's say xg is here, right? If xg is here, we can trace it on the parabola to be here, right? Well, sorry, here. Let's trace it on the parabola to be there. This point right here. And let's just draw the line joining them. And let's get this point closer. Let's say x of g is here. Let me just erase these lines so you guys can see what's happening. This is the tangent. I left the tangent for you. And this point is getting closer and closer to the red point. And the closer it gets, so that was our the third line at this point. And this was our first line, right? And this was our second line. You see what happens as x of g gets closer and closer to x of r? The secant, or if you will, the line joining the 2 points, becomes closer and closer to the tangent of the function. So if it gets very close here, let me just erase these lines. If it gets very close here, let's say you have the point here and here's x of r. and you draw the slope of the secant at them, it begins to look like the derivative or the tangent. Let's get the point very, very close here. Let's draw a line through them. And now it obviously got very, very close to the, if you will, to the tangent. Now, how do you define this in a formula? Well, let's redraw our first secant, which is the line joining the 2 points here. Let's draw our first secant. And let's find its slope. The slope is going to be y2 minus y1. Or actually, let's just call this function f of x. We don't need to call it y2 minus y1 because grade 11. Let's call this function f of x. And let's just let me erase everything and let me show you a different way of representing it, right? So let me redraw the graph. Let this point be x, and let this point here be called x plus delta x. Now delta x is a change in x, a change in x. What does it mean? That means if we have x plus delta x, well, this is basically equal to x plus another number called the change in x, and it could be any number, but it means delta x, a very small change, right? Let's just erase this. So we said let this point get closer and closer to this point, right? As you can see, x does not change. So x and x plus delta x, right? We have delta x here. Now x does not change. As this point approaches this point, as this point goes to this point, very, very close to this point, nothing happens to x because x is x, and it's obvious from the graph. So delta x changes and it gets closer and closer to 0, right? If the point is here, then x plus delta x, and delta x would be smaller and smaller and smaller, right? As soon as delta x becomes 0, then these 2 points coincide. The red point here begins to look like this point, right? And you can see that from the graph. Now, since we have this genius idea of representing the 2 points, we can also represent the slope of their tangent as that. So we started with the secant, and we called this function f of x, right? So we have f of x plus delta x, right? That's our first value, which is this point. And we have our second value, f of x, which is this point. So this is basically y2 minus y1. Yeah, f of x is another way of writing y. And obviously over x, the first value of x is x plus delta x, and the second value is x here. Now we said let delta x get closer and closer to 0, and as that happens, if it goes here, let's say, and then here, what happens is you get closer and closer to the tangent. So if we define the derivative as, let's say, we can simplify this. X plus delta x minus x is basically delta x, right? Because the x's cancel out over delta x, right? Now we said let delta x go to 0. Let delta x go to 0. As delta x goes to 0, we approach the derivative. We approach the tangent, the slope of the tangent, which is there. Now, this is how we define the derivative of a function. We say let delta x go to 0, and we have the slope joining 2 points. And as one of those points gets closer and closer to the other point, as what happened here, the line joining them begins to look like the tangent to the graph. And now we can define this as the slope of the tangent. Right? So let's just erase all of this. And now we have a new formula. So the derivative of a function is equal to that function, the slope of that function, over a small change in x, right? And we say let delta x go to 0, right? Well, in mathematics, we call this a limit. We call this a limit. Limit means one value starts to approach another value. So x starts to approach 0. So we say limit as delta x goes to 0. And that is our definition of the derivative of a function. Thank you guys for watching, and I hope to see you again in another video. And as always, easy.